Good morning. So we'll get started this morning here on some review problems from chapters 3 and 4. If you didn't attend last night's review by Dr. Wynn, if you see my announcement from last week, you can find the video for her review, and you made it. And there's a link to the set of problems that she was working on. This is obviously a different set of problems that I have. If you're looking for the review problems that I'm going to cover here in lecture today, these are at the end of the lecture slide page. I just put them up. I actually put them up last night, but I put them in the wrong place, so you may not have seen them if you were looking for them. But they're at the very bottom of the lecture page. And then there's the couple stoichiometry problems that were still in the chapter 4 notes that I will get to whenever we kind of linearly get to the point of solving stoichiometry. So we're going to look at some review back from early chapter 3 on forward back into chapter 4 here in this packet. I suspect I won't finish all these problems today, so 7:15 Monday morning we'll be here. If you have questions, I will take questions first. So any questions you have on practice exam questions, practice quizzes, homework problems, any topics you want to hear about, we can talk about those issues first. And then if there's no questions or if we need problems to solve, we'll use the remaining lecture review problems here. Okay, so the first question is how many oxygen atoms are present in a 6.5 gram sample of CO2? And so the number of O atoms hopefully can be calculated with a dimensional analysis set of steps. So I start my 6.5 grams of CO2. Then I use the molar mass, the grams of CO2 per mole of CO2. So that's just in the periodic table. So it's 12.01 plus 16.00 times 2. So that's 44.01 grams per mole of CO2. The next question asks down here, how many moles of CO2 are present in that 6.5 gram sample? So if I just quickly do this math here, 6.5 divided by 44.01, that's 0.148 moles of CO2. So that's the moles of CO2 in that 6.5 gram sample. And then 1 mole of CO2 would contain an Avogadro's number, but of what? The what is of what it is. So a mole of CO2 is a mole of CO2 molecules because CO2 is a molecular compound. So you have an Avogadro's number of these molecules. And then 1 CO2 molecule. And now you don't have to picture the Lewis structure. You don't have to know how to come up with the double bonds yet. But a CO2 molecule is literally just a carbon atom and 2 oxygen atoms. So that's what we mean by 1 CO2 molecule. So 1 CO2 molecule contains 2 O atoms. So we just need to do 6.5 divided by 44.01 times Avogadro's number, and then times 2. But this 2 here is an important 2 because it's 2 O atoms per molecule of CO2. And then I arrive at a big number, 1.78 times 10 to the 23 oxygen atoms. And so we can go from mass to moles to molecules to the atoms within a sample. We can even ask a question like this one here, like how many CO2 molecules would be present in grams and in moles in a sample of CO2 that contained 1.0 times 10 to the 22 oxygen atoms. So if we just tell you that a given sample of the molecule of CO2 happens to contain this many O atoms, then we can go the other direction through the dimensional analysis sequence. So let's calculate the number of, let's do the mole first, and we'll convert that to grams second. And so if we start with the given quantity, 1.0 times 10 to the 22 O atoms. The key is that those oxygen atoms are all linked up to atoms per molecule of CO2. So there's 2 O atoms for every 1 molecule of CO2. And then there's 6.022 times 10 to the 23 molecules of CO2 and 1 mole of CO2. So if we hit enter here, so 1 E22 divide by 2, So it'd be 5 times 10 to the 21 molecules of CO2, divided by Avogadro's number. It's 0.0083. Moles of CO2. And so if you think of it the other way around, if you had that many moles of CO2, if you then said how many O atoms does that sample contain, it should be 1.0 times 10 to the 22. You should be able to take this number here and then go this direction forward. So you can kind of go from mass to moles to molecules to atoms, or you go from atoms to molecules to moles, and of course back to mass. And so if we want the number of grams here, this will just be equal to the 0.0083 moles of CO2, and then it's 1 mole of CO2 is 44.01 grams. So that's 0.37 grams. And so that's just some conversion problems relating atoms, molecules, moles, etc., and using Avogadro's number. Just like usual, if you have questions on anything, if there's anything you want to hear more about, just let me know. Well, the numbering here is just weird. These are old exam questions. That's why the numbering doesn't make any sense. But so the question here is, what is the molecular formula of a compound comprised of 87.7% carbon, 12.3% hydrogen by mass, and a molecular weight of 164? These problems are usually like a step one, find the empirical formula. And then step two, find the molecular formula. So we use the percent mass data to get the empirical formula because that's as good as we could do with percent by mass data. You might recall an example we looked at was comparing C2H2, C6H6. They share the empirical empirical formula, and then they have the same percent carbon, the same percent hydrogen. So if you knew the percent hydrogen and the percent carbon of a sample, you wouldn't know if that was the C2H2 or C6H6 or some other compound that had that empirical formula. But then if you could find the molecular formula, terribly written, but the molecular formula is just coming from the molecular weight. And knowing what the empirical formula is. So once you know the empirical formula and you know the molecular weight, we can then figure out how many multiples of the empirical formula are in one of the units of the molecule. And so the reason why I mentioned the step one, step two process is this is kind of the intent of the process, is just trying to show you the process by which we determine formula is by taking data we can get from instruments, can usually furnish the percent mass data, and then we use something like a mass spectrometry experiment to get us a molecular weight. So this is a two-step process. Now, in terms of exam questions, sometimes you'll see an exam question like this, ask for the formula with choices like this, but sometimes you'll just see a question that says, find the empirical formula, how many of the one atom are there in the formula? Like, don't be too confused when you see a problem like this on a test on our Harman system, where the question may seem abstract in the way it's asking you to enter the answer, but the process, I think, is always, from the percent by masses, get a formula. So no matter really what we're asking you, I think the process should be, think of taking the percent masses into a ratio of moles, try to get the simplest whole number ratio of moles. And if we ask you just to maybe enter the coefficient or the subscript for one of the atoms, you still need to determine the other. So just know that there's, a process here by just taking the ratio, say of 87.7 grams of carbon in ratio to 12.3 grams of hydrogen. I just have to start with two masses here that have the proper ratio. And the easiest way to come up with that ratio is just to take the percentages as masses. And so if a sample is 87.7% carbon, 12.3% hydrogen by mass, and that would be represented by a sample that's 87.7 grams to 12.3 grams carbon to hydrogen. And so we just want to go from the ratio of the masses to the ratio of the moles. And so I just go 12.01 grams per mole of carbon, 1.008 grams per mole of hydrogen. So I go from a mass ratio to a mole ratio. It works out to be 7.0 302, and then the hydrogen, 12.20. And now I think it's important to remember that's the mole ratio or a mole ratio. Specifically, it's the mole ratio of a 100-gram sample. So we want the nearest whole numbers. Can I round to 12 and 7? I wouldn't yet, so we got to be really close to whole numbers here. So to be able to round, so let's divide by the smallest. So let's divide both of these by 7.302. I can't divide them by different numbers because I'd break the ratio, so I got to divide them both by the same number. I at least get a whole number in the place of carbon, so that gives me 1 mole of carbon in ratio to 12.2 divided by 7.302 to 1.67 moles of hydrogen. And then I need to think multiples. Obviously, like a fraction wouldn't work because then the 1 mole of carbon becomes a fraction again. I don't want fractions, I want whole numbers. So I have to take these ratios and start thinking, can I double them and get whole numbers? Not quite, so 1.67 times 2 doesn't end in a whole number. So then I think times 3. Does that work? If it didn't work, I would just keep going. 3 should work. 1.67 times 3 is equal to 5. And so this gives me a ratio of 3 moles of carbon to 5 moles of hydrogen for an empirical formula, the simplest ratio of C3H5. If I wanted to, I could double check this. You know, like you could just say, well, what's the percent carbon in C3H5? And it would be 12.01 times 3, divide by that formula weight, and we should come back to the 87.7%. So you can easily double check your work here if you wanted to, or if you get a formula that doesn't look quite right, you might go back through your steps and try to see, did we make, you know, a math error somewhere? But moving forward with C3H5, the next question would be, well, what's the empirical formula weight? So what's the weight of that formula? So just 12.01 times 3 plus 1.008 times 5. That's 41.07. This is getting at now into step 2, where once I have the molecular weight, which is 164, so the 164 molecular weight, I want to divide that by the empirical formula weight to see how many multiples there are. So it's 164.3 AMU, divide by 41.07 AMU. A quick little sidetrack on AMU versus grams per mole. Just know that the empirical formula weight, we can write 1 of 2 different units here that are somewhat interchangeable but have slightly different meanings. And the meaning is this. So the C3H5 formula, if you take the mass of 3 carbon atoms and 5 H atoms in atomic mass units, a single connection of those atoms, a single unit of those atoms would have a mass of 41.07 AMU. So a molecular weight or an empirical formula weight is the weight of just those atoms in that unit of AMU. If you were to convert this to grams, it would be an incredibly small mass. The AMU to gram conversion, if you recall, is Avogadro's number of AMU per gram. So this would be on the order of 10 to the minus 23 or minus 24 grams. So a really, really small mass for just those atoms. But then if you go grams per mole, 41.07 grams per mole, that's just the molar mass. That's how many grams a mole of that formula would represent or would contain. And so anyways, we get a multiple of 4. 164 divided by 41 is 4. And so our formula will be C 3 times 4 and then H 5 times 4. So the formula should be C12 H20. And so again, these problems here are kind of usually, can we get an empirical formula from percent by mass data? If we had an ionic compound, usually all we want is the empirical formula. But if you see a compound that contains non-metallic elements like CH, N, O, etc., those formulas, we usually want to know the molecular formula because that's really what's special. That's what makes a molecule special is its molecular formula. What really makes a molecule special is its molecular structure. But for now, the best way to then get into the structure is to see what the formula is. So get the formula, then see what the structure is. We'll learn about that later in chapters 8 and 9, and then you'll see a lot about it if you take OChem. Okay, so moving on into some stoichiometry problems. So nitrogen gas reacts in a closed container according to this reaction to form ammonia. So N2 and 3 H2s react to form 2 ammonias. And so this reaction is balanced here. So what it looks like initially might be a collection of nitrogen atoms, and then we have a collection of nitrogen molecules and hydrogen molecules. You made it. And so I do that too. I have like 50 alarms set in the morning as well. But so if we imagine lassoing out like an N2 and 3 H2s, then those are the connection of atoms that should be able to react together to then produce 2 NH3s as a result. And so the question is asking based on these amounts in this box here, what should be present after the reaction goes to completion? So if the reaction in the box here goes to completion to form ammonia, what should we get? Well, the atoms I've circled would be replaced by 2 ammonia molecules. And so I should have 2 ammonia molecules in my product box. And so then what else should I have? I have 3 more H2s here. It's kind of hard to sketch since, let me start over one more time and see if there's a better way I can sketch these. So what if I take these 3 here to get the 2 NH3s, and what if I take these 3 and the N2 here to get 2 more NH3s? And then I have the N2 left over because it looks like I have 1 extra N2 from what I really need in this reaction. So my N2 is my excess reactant here. Hydrogen's present in the perfect quantity to react with 2 of the N2s, 2 of the 3 N2s. And so we're left behind with an N2 here and then 2 NH3s. And so in terms of the box, of course, that would look like box 3, where we have the molecules of NH3 and then the N2 left over. And so what box 3 is kind of also showing is that when we see like the 2 NH3, that's 2 distinct molecules of ammonia. Like these here, let me use this pen here, that's not NH3. Like when you start thinking of 2 NH3, it just means 2 separate molecules of NH3. If you wanted to show something that looked like these molecules here, that might be N2H6, which is a different molecule, would have a different description. We'd write that specifically into the product if that was what the formula of the product was. So that's why box 5 is wrong. Box 4, of course, is wrong because we don't have a leftover H2 molecule. 2 is just missing atoms anyways, and then 1 doesn't show the leftover reactant. And so particle diagrams are a type of question that kind of like allow us to see at a molecular or atomic level what might go on in a reaction, where we can actually picture the reaction taking place, think of the reacting units. You can still work through this problem with math. I won't show the math, but you could still say 3 molecules of N2, how many NH3s should I get? It should be for every 1 we get 2. So we would have, if all the N2s were able to react, there should be 6 product molecules, but if all the H2 react, only 4. So you can think through this problem here with dimensional analysis too and some of the other thought processes, but obviously it's probably easier to sketch out and use the diagram on those problems. Moving on to this one here, so this gets just back into dealing with more ordinary masses and probably using dimensional analysis. But so here we have Cr reacting with O2 to produce Cr2O3. The reaction is written in balance for us. So if we have 39 grams of chromium, 16 grams of oxygen combined, based on the theoretical yield, this is not my favorite way of saying this, but this is just saying, assume the reaction goes to completion. So assume the reaction produces as much product as possible. And so once the reaction's completed, according to the coefficients of the reaction, according to the stoichiometry, which reactant remains and in what amount. So this problem here is just asking for us to identify which reactant is the excess reactant and how much of it is left over. Now, there's more than one way to figure out the limiting versus excess reactant. The one method that comes to mind to, I think, a lot of you guys, and this is a fair way to find the limiting versus excess reactant, is just to take the 2 reactants and see which one makes less product. So just consume all the chromium, make product, consume all the oxygen, make product, which one makes less, that's your limiting reactant. You could do that, but then we'd have to do a second math step afterwards to figure out then how much of the excess reactant is consumed, how much of it is left over. So it becomes maybe a couple extra math steps. So what I can also then do is I could set up a BCA chart. I'm not going to do it, but I could if I wanted to. And if I were going to do that, I would probably convert the mass of chromium to moles, the mass of oxygen to moles, and have my BCA for those, the minus 4x for chromium, minus 3x for O2, and try to figure out which one goes to 0. And if, so that would allow me to determine X, Then I can determine the other one, see if it's negative or positive, that kind of deal. And so the other thing I can do, probably the fastest way to solve this problem using dimensional analysis would be just to say, well, how much of the just choose one of the reactants. Let's pick the O2. How much O2 do I need to react with the given chromium? And so the mass of O2 that needs to react with the 39 grams of chromium, if I pick right, then I just have to do this problem one time. If I pick wrong, I'll just run through it by flipping the chromium and the oxygen around. But I start with my 39 grams of chromium. I need the molar mass of chromium. It is 52.00. 52 grams per mole. And then for every 4 moles of chromium that reacts, I need 3 moles of O2 to react with it. 1 mole of O2 is 16 times 2, 16.00 times 2, that's 32 grams. Okay, so I did not get lucky and pick the right limiting reactant to start with. I get 18.00 grams of oxygen's needed. Now, how I know I picked wrong is I only have 16 grams of oxygen. So in order to consume all the chromium, I need 2 more grams of O2 than what I have available. So I look at the mass of O2 and I say, that's not gonna work. So what I need to do is just flip this around. And the reason why this was a good starting point, though, was if I had just, I had a 50-50 chance of choosing the right limiting reactant from the start. If I had chosen right, I'm just doing a difference of how much reacts, how much is available, to how much is remaining. So all I have to do here is flip the problem around, see how much chromium I need to react with all the O2. 32 grams per mole of O2. For every 3 moles of O2 that react, we need 4 moles of chromium to react with it. That's 52 grams per mole. So I get 34.67. So that's the mass of chromium I need to react with the O2, and I have 39 grams, so that's good. The number of grams of chromium that remain will be equal to my initial amount minus my amount that reacts. So that's 4.33 grams. Now, a few things. One, the tendency is to not write the math out for some reason. I think the tendency when you're taking an exam is to want to go quickly and to try to do some of this math in your head. I think this step here in particular is very easy to flip if you're not being careful and writing it out. And so unless you're really, really good, unless every time you take a practice test, you're kind of doing the work in your head and getting the right answer, unless that's the case, I would probably take the time to be meticulous and write the work out. And sometimes you might catch a mistake in your mind that you may think a step goes a certain way, and if you're writing the dimensional analysis out and just trying to do all these conversions, and maybe sometimes I don't take the time to show how everything cancels, but if you're taking the time to make sure that when you have mass here, it's here, moles here, it's here, chromium's here, it's there, like that dimensional analysis step will help us get towards the right answer. And if we're not writing it down, sometimes we may flip things very easily. And also, I just wonder how often when you guys do homework, you don't write things down. So I don't know, I just happened to be sitting with my daughter the other day. She's 6th grade doing her math homework and she wasn't writing anything down. And I'm like, how can you even do fractions and division without having a piece of paper in front of you? So my recommendation, make sure you have paper or something to write on available when you're doing your homework, just to write the work down, even if it's chicken scratch, sloppy work. As long as you're thinking and processing the numbers and seeing the math, how it works, I think that will be beneficial to you. And like I said, if you're getting things right without doing that, that's great. If you're missing some problems on your practice tests, on practice homework sets or quizzes or whatever, then think about just writing a few more things down. Okay. So this question here is giving us the H2 plus O2 goes to water reaction. Everything's a gas here, so gases and the reactants and products. And so we're told that after the reaction is complete, 6 moles of water have been produced. And so we're told hydrogen and oxygen gas combine to form water in a closed container. After the reaction is complete, there's 6 moles of water that have been produced, 4 moles of oxygen remain. And based on the theoretical yield, again, assuming that the initial reactants reacted to produce the product to 100% yield, so assuming just the stoichiometric yield of the reaction, how many moles of gas were initially in the container? Now this is kind of a strange question. I remember when this is on a test and I was thinking, this is kind of abstract the way this is asking the question, because what it's trying to get you to make sure you see is that initially we have the 2 reactants, none of the products. And so initially just H2 and O2. And so we know, but we don't know how much of either was initially present. And then we just know that after the reaction, we have 6 moles of water, and then 4 moles of O2 remain. And then because of the whole, like the reaction went to completion, the O2 is remaining, the H2 has to, after the reaction completes, be 0. So after the reaction completes, we have no hydrogen left over, we have 4 moles of oxygen that are left over, and then we have 6 moles of hydrogen that have been produced. The author of this question really wants us to use a BCA chart, and let's avoid it. Let's try to not use a BCA chart. And then maybe afterwards, this will be the one time I do show a quick BCA chart and how it might be useful to think in this problem here. So from the 6 moles of water that were produced, we can ask the question, how many moles of oxygen did it take to produce that quantity? So 6 moles of water is produced in this reaction. How many moles of oxygen did it take to produce that quantity? For every 2 moles of water that form, we had to consume 1 mole of O2. So that means that 3 moles of O2 were consumed during the course of the reaction. And so that has to mean that we initially had 7. Because if we had 7 moles of O2, we lost the 3 that react, we then have the 4 moles that are left over after the reaction is completed. And so if we think the initial moles of O2 minus the reacted moles of O2 equals 4 moles, because that's what remains, and then this amount here is the 3 moles, that's how I determine that this must be equal to 7.0 moles that had to initially have been present. So I'm deducing there must have been 7 moles of O2 present in order to react with the hydrogen to produce the water. Okay, so that's the 7 moles of O2. What about hydrogen? How many moles of H2 were consumed to produce the 6 moles of water? For every 2 moles of water, just from the reaction, so just looking at the coefficients in the reaction, for every 2 moles of water that are produced, we have to consume 2 moles of H2. And so that means that we had to initially have 6 moles of O2, or 6 moles of H2, in order to react with the 3 moles of O2 to produce the 6 moles of water. So 6 moles of H2 initially had to be present, and then they're completely consumed, so it's down to 0. So my initial H2 minus the reacted H2 has to equal 0 because there's none of it left over, because one of the 2 reactants, if the reaction hit its theoretical yield, one of the 2 reactants had to be consumed. So the hydrogen's the consumed reactant because the oxygen was left over. And so we had to have 6 moles here that reacted, so we had to initially have 6 moles available before the reaction started. Okay, so initially here we would have 7 moles of O2 and 6 moles of H2. And so the answer to the question here is 13 moles. Tricky question, but it's tricky in a sense of just like thinking through the dimensional analysis. I think the tricky part is just knowing how the initial and the reacted connect to each other. That when we're producing the water, we're trying to figure out how much reactant had to be consumed. In order to have consumed the reactant, it had to be present. And so if we go back to a BCA chart, this might actually make things make more sense, I hope. So if we're thinking of this 2H2 plus O2 goes to 2 water, and we go to the BCA chart. This problem here is kind of wording it this way, where it's like, we don't know these two amounts here. We just know that this is a minus 2x, a minus x, and a plus 2x. And that initially there's no water. That's another detail we know, is that there was no water initially present, because we're told you have H2 and O2 in the container. They react to produce the water. So initially no water. Then we get the 6 moles here. And do you see how right off the bat on the BCA chart you can find x? Like, you can find x is equal to 3 moles. Just 0 plus 2x is equal to 6. So 2x is equal to 6 moles. So x is equal to 3 moles. And so we also know that after the reaction is complete, we have 4 moles here, and then we have none in the place of H2. And what we wanted to know, what's the sum of those initial gas moles that were present? And so if we're getting to 4 moles here, we know x is 3. That's how we know this must be 7. In order for H2 to get to 0, minus 2 times 3. So we have to have 6 minus 6, 0. So 6 moles for H2 plus 7 moles for O2. So you can get there with the BCA chart. The BCA chart might be helpful just to think initial reactants being lost to make the products. So initial reactants going away, products gaining. I think they help us understand what's going on in these steps here and here. That what those steps are saying, when water is being produced, when 2 moles of water are being produced, a mole of O2 is being consumed, provided we have enough H2 for it to react with as well. So there's a lot going on in these steps here that if you're not thinking of the full reaction and maybe something like a BCA chart in your mind, then you may be struggling to understand the simplicity of stoichiometry. Okay, so that problem's kind of tricky, but I think it has a good solution that helps us understand some different details of reactions if we weren't thinking along those levels. Okay, so let's move into chapter 4 with some topics here. So we're told here an aqueous solution of nitric acid, the problem says, an aqueous solution of HNO3 is a strong electrolyte and therefore an excellent conductor of electricity. Which of the following diagrams most appropriately depicts the particles in this solution? I'm not even sure we need to tell you this sentence here. You know, like, we would expect you to probably know that detail, that HNO3 is one of the 7 strong acids, meaning in water, it would be dissociated into H plus and NO3 minus completely. And so then what diagram shows what you think nitric acid would look like in water? And the water molecules themselves are not being shown, so you're not being shown the actual water molecules, but this is kind of a depiction of what this molecule might look like in water. And so if you're thinking box 3, let's start with box 3. Why is this one wrong? Well, that would be showing the H plus and the nitric acid molecules intact, and I don't see any ionization at all. This box here looks like a non-electrolyte. That's what we expect if nitric acid didn't dissociate at all in the solution. If we had something like methanol, methanol doesn't dissociate in water. Methanol would just be the molecules of methanol. It wouldn't be H plus ions and some sort of anion. So box 3 is wrong because HNO3 is an electrolyte. Now box 4 might be what we're thinking if we're not sure what nitrate does. Does nitrate turn into nitride and oxide ions? It does not. Nitrate's a stable ion, and so we're not going to have the dissociation of the nitrate ion into like N3 minus and O2 minus or any other peculiar ions like that. And so then what nitrate would look like is probably something like this, where we have a negative charge, where we have a ratio of like N and 3 O's somehow sharing a negative charge. Where the negative charge is kind of spread across the molecule, so it might be hard to depict that in a diagram like this. But this is really starting to look like, you know, where we have 1, 2, 3, 4, 5 molecules shown. We have 1, 2, 3, 4, 5 H plus ions. So box 1 is looking like the best answer. And so box 1 is the answer. Box 2 is wrong because it's looking like what a weak acid would look like. So box 2 is depicting a weak electrolyte. It might be what a solution of HNO2 would look like, because HNO2 is not one of our 7 strong acids. Its name is nitrous acid. And so if you had a sample of HNO2, you would expect, maybe, one molecule out of 10 is dissociated, the rest are associated as HNO2 molecules in water. And so this might be a depiction of a weak acid, weak electrolyte. So weak acid, weak electrolyte, HNO2 perhaps in box 2. So box 1 would be the answer here. Now let's think about a bunch of different types of compounds. I'll probably give more examples than these ones here. But let's think about the electrolytic nature of these compounds here in water. Let's actually start first with the description of MC or IC. Is it molecular or is it ionic? Because if we're getting that wrong, then we might be picturing a few other things wrong. And so let's make sure that when we look at KOH that we're picturing this as an IC, metal, non-metal. So that's definitely an ionic compound. The compound in 2 is all carbon H&O. That's a molecular compound. Compound 3 is a molecular compound. Lead's a metal. Like we get into the metalloids, kind of separating the metallic, non-metallic, but lead's still on the metallic side. So that's an ionic compound. And so then we also think of it as lead 2 plus, I minus. So you can start to think, is it comprised of ions and the way we think and describe the compound? And so the ionic compounds, we then can use a solubility chart. You get the solubility chart on the exam. If you look at the practice exam went up yesterday, in the area you will see the sample info you get for the exams. You get a slightly different typed version of the solubility chart, but the exact same information from the solubility chart we showed in class. And so you can see PBI2 is insoluble. So the next question would be, for the ICs, are they soluble or insoluble in water? And so KOH is soluble in water, but the PBI2 is insoluble in water. Now, water solubility for molecular compounds isn't something we get from a solubility chart. What we get from compounds that are in water tend to be alcohols, acids, and then we generally are like by the nature of the question for the molecular compounds to consider its behavior in water, you're kind of assuming it's in water. So we're really not predicting solubility trends for the molecular compounds like we do for the ionics. So for ionic compounds, it's important for us to think water solubility. So yes, here for water soluble, and no for the PBI2, because the PBI2 then is a solid, not dissolved in water. So PBI2 is not any kind of electrolyte in water because it's not in water. It's like not applicable to give it a term for a solute when it's not a solute. So it's like not in the solution at all, it's insoluble. And so there's no electrolytic behavior at all for PBI2, definitely not a strong electrolyte, but OH is a strong electrolyte. So all water-soluble ionic compounds dissociate, so KOH being one of those. So KOH should dissociate into K+, and then the hydroxide ion. The ions that you learn how to name stay intact in water, so phosphate would stay as phosphate, hydroxide is hydroxide, sulfate is sulfate, nitrate is nitrate, acetate is acetate ion, etc. And then what about the compounds in 2 and 3? Let's start with 2 first. So 2 is by name acetic acid. You can see in the word it's an acid by its nomenclature. That's why I think we stress nomenclature first, is so we recognize the formula as being acetic acid. And then this group here is what makes it acidic. The COOH group is an acidic functional group in organic chemistry. And so we recognize that group as being acidic. I wouldn't, I only stress that so that when we look at methanol, we see that this is not acidic because it's missing that CO piece. We need the COOH to be together in order to have an acid. And so this here is not an acid or base. How do we know it's not a base? Well, the only base that we learned from formulas that we recognize from nomenclature is ammonia for the molecular compound side. So if you're picturing a molecular compound and saying for acids that we learn how to name, for alcohols, hydrocarbons that we learn how to name, remember binary compounds like CO2, CO, those type of compounds, the only ones of those compounds that acts as a base that's common for us to recognize is NH3. And it's a weak base, weak electrolyte in water. And so the thought should be for like methanol, not an acid by nomenclature, so it's not acidic, not ammonia, so therefore it's not a weak base, so it's not any kind of base either. So therefore the solution of methanol would be a non-electrolyte. And then the acetic acid in water would be a weak acid because it's not one of the 7 strong acids. So what are the 7 strong acids? That's something you just have to memorize. So it's HCl, HBr, HI, the key being not HF. And then I think it's key to seeing that the acids begin with HCl because then it's HClO3, HClO4, and then HNO3 nitric, and then sulfuric, H2SO4. So those are in the notes if you want to see them written out. And it's only the first hydrogen off sulfuric acid. And then sulfuric acid is the only diprotic acid. All the others are monoprotic. I'll write them real quick. HCl, HBr, HI, HNO3, and then think chlorine here, HClO3, HClO4, and then its neighbor, H2SO4. And then, some missing acids that aren't on the list here, like phosphoric, carbonic, all the us acids, nitrous, chlorous, etc. And so these are the only 7 strong acids. And so that's how we know that the CH3COH must be a weak acid, and it's a weak electrolyte because it partially ionizes the H plus and acetate ion. So weak acid, weak electrolyte. So it's certainly not a strong electrolyte. So the only strong electrolyte here is 1. And so, yes? So all of the strong acids do end in ic acid, so there's no OUS acids. Yeah, but it's not all of the ic acids. Being a ic acid doesn't make it a strong acid, but to be a strong acid, you do have to be an ic acid. Does that make sense? Yeah. So that's why I'm saying like phosphoric. Like if you think of when we were learning how to name these things, we were doing like these, like carbonic, nitric, phosphoric, sulfuric, chloric, and like these are not in the strong category. It's just these, and it's the ClO3 and the ClO4. Okay, so which group of compounds here are all weak electrolytes in water? So weak electrolytes, if we think of things that, what things are capable of being weak electrolytes? And there's 2 basic categories. They're the weak acids and the weak bases. And so those are the 2 different categories of compounds that fit the bill of being weak electrolytes. If you then think of what these categories are, these are all molecular compounds, or at least from the way we understand these compounds, the way we presented them to you, the ones you can recognize are all on the molecular compound side, and then none of them are ionic. Because the thought is if it's an ionic compound, it's either water-soluble strong electrolyte or it's insoluble, not in water. So if you look at something like MgOH2, the only question for MgOH2 should be, is it soluble? If so, it's a strong electrolyte, or is it insoluble, therefore it's a non-electrolyte, not even a non-electrolyte. A non-electrolyte is something that's a solute that doesn't ionize. MgOH2 is just a solid floating at the bottom of the test tube and isn't dissolved at all. So MgOH2 cannot be a weak electrolyte. It can either be a strong electrolyte if it's soluble, but it's insoluble according to our solubility chart. So this thing here is not any kind of electrolyte. It's not applicable to call it an electrolyte. Ammonia and HF are weak, but A would not work because of the magnesium hydroxide. HCl and HBr are strong electrolytes because they're strong acids. HClO3 is a strong acid. This looks good. So we have the weak base, ammonia, 2 weak acids here, nitrous and phosphoric. So D looks good. And then we do have a weak electrolyte for acetic acid, but not methanol. That's non-electrolyte. Sugars are key examples of also being non-electrolytic in water. So they're not causing light bulbs to light up. Remember we did the light bulb demo. Does the light bulb have ions? Does the solution have ions that link a set of electrodes in water to allow a light bulb to light up? If you could put a piece of copper between the electrodes, it would light up. If you have ions in the solution, they'll conduct the electricity from one electrode to the other, but not water itself and not just a non-electrolyte. So we had a sugar water example and it did not cause the light bulb to light up. So no ions here for something like a C6H12O6. I think when you see a compound like that, we're representing something like glucose, C12H22O11, sucrose. So those are just simple sugars. So just D here. Consider the reactions of barium hydroxide and potassium carbonate in water. So there's aqueous solutions of these compounds. Which of the ions are spectator ions? So let's think of the reaction here. Now I don't have to think too hard about solid or AQ for the reactants because I'm told we have aqueous solutions of those things. Barium hydroxide is water soluble. Barium is one of the exceptions for hydroxide ion. K2CO3. Anything with potassium is water soluble. The one solubility rule that's not on the chart, that wasn't on our chart either, was like a little footnote below it, was that all ionic compounds of ammonium and the alkali cations are water soluble. So if you see K plus with anything, it's water soluble. Doesn't matter what the anion is. If you see like lithium, sodium, rubidium, cesium, ammonium, any anion they're paired up with is going to be water soluble. Did I see a question? I wasn't sure if you, okay, cool. And so again, so AQ here for K2CO3. And so then our product here, let's switch out our two cations with each other and exchange them for each other. A lot of times we call this an exchange reaction for that reason. And so one of the products would be barium carbonate. And then the question is that solid or AQ? We would go to the solubility chart. Barium carbonate is insoluble in water. So that's definitely going to be a solid, meaning it's going to precipitate out of the solution, form a solid. And then the second product should be the other thing, the KOH, which is an AQ, water soluble. To balance out, I need two KOHs, and then I think I'm in balance here. And so then this is the balanced full molecular reaction. Now we call this the full molecular reaction because the AQ ionic compounds are really not molecularly linked together in solution like we're showing them. And so the things we can do is we can write the full ionic equation, which looks like this: barium 2 plus 2 hydroxide ions. I'm dissociating my strong electrolytes. So the only things I dissociate are strong electrolytes. So is barium hydroxide a strong electrolyte? Thought is ionic or molecular? It's ionic. And then if it's ionic, is it water soluble? If so, it's a strong electrolyte. And so we're dissociating the strong electrolytes. And the only other category of strong electrolytes that aren't ionic are the 7 strong acids. So the only things I dissociate in a ionic reaction are water soluble ICs and strong acids. And so I get my 2K plus carbonate ion. These are all AQs. I'm neglecting writing AQ a bunch of times, but the one that's not separate is barium carbonate because it's not a water-soluble ionic compound. It's the insoluble compound, so it stays intact. And that's the whole idea, is that it's forming barium carbonate, not breaking back apart. K plus forms from the 2 KOHs. And so because KOH is a water-soluble ionic compound. So I'm dissociating my water-soluble ICs and strong acids. And so my spectator ions are the ions that are in identical form on both sides of the reaction. So that's hydroxide and that's potassium. And so the spectator ions here would be the potassium and the hydroxide ions because they appear in identical forms on both sides of the reaction, meaning they're just watching the reaction is the thought. And so we can cancel them out. The spectator ions don't appear in the net ionic equation. So let's identify here. So we have the full molecular first. Then we have the full ionic. Then we have the net ionic. The net ionic here being barium 2 plus carbonate 2 minus. If we want to be technical, we would write AQ. Again, it kind of makes it hard to write it for the full ionic without being completely distracting. But we write those in for the net ionic here to show barium ion in solution, carbonate ion in solution bump into each other. A bunch of them form the solid, and it crashes out of the solution as that solid precipitate. And so the whole point here, I believe, of identifying and writing net ionic equations is just to see, is there a net change? You were really just trying to see through this process here, is there really a net change going on? Because if I don't have this thing here form a solid, if that compound happened to be aqueous and it was barium and carbonate ions too, then there's really no reaction taking place. So answer E, it's really helpful for us to make sure that we can rule out that being the answer by identifying something that forms that doesn't then break back apart. So in any reaction from chapter 4 that we've talking about net ionic equations, primarily these reactions, so the precipitation reactions, but the other one being acid-base reactions, the key is forming a compound that doesn't dissociate. So water insoluble IC is one of those examples. Forming water because it's a non-electrolyte and an acid-base reaction is a good thing to form. Forming carbonic acid because it dissociates into CO2 and water. Probably not exactly a reaction I expect you to predict just randomly by writing, but whenever you form a gas in a reaction, it floats away and can't possibly go backwards. Yeah.
Now, if you were to have a weak acid, let's say as a product, would that be a spectator? Because it, like, only partially dissociates.
Yeah, so like if you had the acid-base reaction of like HF plus KOH, and these are in water, and we know that we should form the swapping of these here, so we should be forming KF, the salt, and then, which is water soluble, and then water liquid. And so the key here, yes, is that we don't dissociate HF. So we only dissociate the strong electrolytes. And so in our full ionic equation, we leave HF as AQ. And I think like when we say full molecular reaction, don't think that we're saying to like make everything ionic that's not necessarily a strong electrolyte. So we're still saying only dissociate the strong electrolytes. And so we leave HF as HF, K plus we can separate, KF we can separate, and then water, non-electrolyte, we leave as water. So in terms of our electrolytic behavior, weak electrolyte, strong electrolyte for KOH, strong electrolyte for KF, non-electrolyte for water. And so we're only dissociating the two strong electrolytes. So we'd only have one spectator ion here, which is potassium. So you don't have to have a balance. You don't have to have a plus and a minus to be the spectator ions. We can have both of them. In this case, just be the potassium. So the net change here, just HF AQ plus OH minus AQ forms F minus AQ plus water liquid. But you turn this into HCl. HCl is a strong acid, it dissociates, and then we'd be dissociating HCl at this step here. So our strong acids we can dissociate, strong electrolytes. For the water-soluble ICs we can dissociate. I think the next slide, at some point there's a slide on the summary of a bunch of different reactions. So let me look at this question, then I might look ahead to a question to try to summarize a bunch of different reactions here. So oxidation number rules, how do these work? Well, just remember if you have an element, elements are just zero. So sodium solid, 0, Cl2, 0. So that's C would be 0. HCl, hydrogen's plus with molecular compounds, it makes chlorine minus, so plus and minus for HCl. We're looking for chlorine with a +1 oxidation number. We don't get there with C or D. NaClO, so sodium's always a plus, meaning the whole ClO minus is a minus. If you recognize that from nomenclature, that's the hypochlorite ion. ClO minus, we learned how to name back in chapter 2. But the way we can assign the oxidation number is that oxygen has to be -2. By rule, oxygen's -2 with some exceptions, and this isn't one of the exceptions because the exceptions are compounds with F, it's not F. And then oxides are, peroxides or superoxides, that's not one of those. So this is just oxygen with its normal rule of -2. And so then that's going to have to make chlorine be plus. So we can have sodium be +1, chlorine be +1, -2 for the oxygen. NaClO is uncharged. The overall molecule of NaClO is neutral. So these all have to sum up to 0. And so B is the one with chlorine being 0. Let me look at ClO minus again separate, because if we're then saying, well, hold on, wait a minute, let's make sure we're understanding this right. If oxygen's -2, chlorine here is positive, +1 -2 is equal to -1. That's the charge on that ion. So you see how if you break it apart into its ion, we still get +1. And then ClO3, +2, -2, ClO3 to a -2, -6 here for the 3. Has to be a +5. Sorry to skip here. I was, oh, yeah. Apparently I didn't put the page in the notes I thought I did, or somehow I missed it. There, I'll talk about it on Monday, but there's a summary of the 6 reactions. I'll just give you the quick names just to wrap up today, because we have 6 key reactions. I just want us to make sure to hear these today. Chapter 3 had 3 reactions. Combustion. Hydrocarbons combust to form CO2 and water. That's easy. We can balance that out. We have combination reactions. Elements can combine to produce compounds like Na and Cl to NaCl. depending on metals and non-metals, we can predict the charge states. If we give you like an alkaline, we know it's going to form a +2, chlorine a minus, so we can predict a few products there. Decomposition are things that fall apart into multiple things. And then we have the metathesis, acid base, and the redox reaction. So we'll review a little bit more about the redox next time, or you can spend some time this weekend if you wish, reviewing some materials. So I'll see you guys on Monday. Have a great weekend.
I have a question for you.